All right, this is a brief tutorial on electrostatic force in terms of charged particles. So let's look at a basic problem here. We got two positive charges, which means they're going to repel. So there are two positive charges. One is 2 microcoulombs, and the other is 7 microcoulombs, where micro is 10 to the negative 6. They are going to repel one another because they're both positive. Recall, same charged particles repel, oppositely charged particles attract, meaning that if I had a positive and a negative, they would both be attracted towards one another. So if we look at the problem specifically, the force acting on the charges is equal to a constant times the first charge times the second charge divided by the distance between them squared. That means if the distance doubles, then the force is reduced by 1/4, etc., etc. The constant, the K, is 9 times 10 to the 9th newtons meters squared per coulomb squared, where a coulomb is a joule per volt if you want to break the unit out. Now, we need to get these microcoulombs into coulombs so the problem units will work out. So it's going to be 2 times 10 to the negative 6 coulombs. Remember, micro is 10 to the negative 6. And 7 times 10 to the negative 6 coulombs for the other. Coulomb is actually a very large charge unit, and so a lot of times you do see, in fact, see microcoulombs, which is why it's presented here. Divided by the distance in meters, so 0.20 meters, and that is squared. The meter squared is going to cancel, and the coulomb squared is going to cancel. And then it's just a matter of running that through your calculator. So you get 9 times 10 to the 9th times 2 times 10 to the negative 6 times 7 times 10 to the negative 6, all divided by 0.2 squared. And so our electrostatic force in this case is 3.15 newtons. And that would be our electrostatic force in this particular case. Next, we have a slightly more complex problem. We've got 3 positive charges in a line. And so they're all positive charges, which again means they're all going to repel. The distance here is 1 meter. The distance here is 2 meters. This is 0.02 coulombs. This is 0.10 coulombs. And then this is 0.04 coulombs. So smaller charges, but a smaller distance versus a larger charge with a bigger distance. So which is going to come into play? So let's look at our options here. So for A, we're going to look at the force of attraction between these two. So the force, use the same equation as the previous problem, 9 times 10 to the 9th newtons meters squared per coulomb squared. We got 0.02 coulombs and 0.10 coulombs divided by 2 meters. So we're going to run that through our calculator once again. And we're going to get a rather large force of attraction, because notice the coulomb charges are actually that much bigger. Remember to square your unit on the bottom so that the units work out. So we're going to get 4.5 times 10 to the 6th newtons. So that would be the answer to A. For B, it's going to be the same equation. So we'll do it a little bit more quickly now, but we're going to use the forces from the other side. We'll divide by 1 meter quantity squared. So we're going to get 9 times 10 to the 9th times 0.02 coulombs and 0.04 coulombs. The 1 squared in the bottom doesn't do much for us, but we get 7.2 times 10 to the 6 newtons. Notice that even though there were smaller charges, they're a lot closer together, so you do get a bigger force. Now, since they're repelling, that means the net push on this particle will be in that direction, which means to the left. So what's the magnitude? It's just the difference in there, the 7.2 minus the 4.5. So you get 2.7 times 10 to the 6 newtons, or 2.7 meganewtons to the left. That's been a brief tutorial on electrostatic force.